Welcome back, everyone. In this section, we're going to talk about statistics. Data are measurements or observations that are collected for some event or phenomenon that we're interested in studying. Statistics is a branch of math that just involves collecting, organizing, summarizing, and presenting data, and then using that data to draw conclusions. In statistics, we start with a question that we'd like to answer, we gather data, and then we try to interpret that data in order to answer our question. Ideally, if we wanted to answer a question such as the average GPA of a college student, we'd want to collect the data on every single college student in the country or in the world, depending on what we were interested in. This would be considered the population of college students. A population just consists of all the subjects that are being studied in particular research. However, for most questions, you'll collect data on a subset of the population known as a sample. If a sample is a good representation of the population, then we don't need to collect data on everyone. The sample will give us enough information to answer our question about the population. So there are four basic ways that we can sample particular populations. The first is what's known as a random sample, and this is where every member of the population has an equal chance of being selected for the study. One way to choose a random sample would be to essentially assign every person a number and then have a computer or something else randomly choose a number, and those numbers that are chosen would be the ones that make up your sample. In this way, every person has an equal probability of being selected. A systematic sample involves numbering every member in the population, but then you want to choose every kth member of the population, where k is just some natural number. 1, 2, 3, 4, 5, and so on. For example, you number everybody that you're interested in, and then you choose every 10th participant, or every 10th person on the list. If you have a population that's divided into groups, where some of the members of each group are going to have similar characteristics, for example, large public schools, private schools, small public schools, and small private schools, we can choose members of the groups at random. And the result we get is a stratified sample. So we go to a bunch of large public schools and choose a sample at random, go to large private schools, choose a sample at random, small public schools, and small private schools, and we just take samples from all of them. Medical researchers often stratify samples by dividing subjects into gender groups, age groups, racial groups, or many other different categories. They'll divide them into those groups, and then they randomly select from those groups. The final way we can collect a sample is what's known as a cluster sample. Here you might sample one component of your entire population if you can assume that that component will represent the entire population. For example, an inspector might want to check some manufactured materials to look for defective items, and so the inspector will just choose one carton of a particular item and then check every one of the items in the carton. That carton would represent the cluster. The inspector is then assuming that this cluster of items is the same as every other cluster of items. And so if he can figure out how many items might be defective in the cluster, he would have a pretty good idea of how many items would be defective overall. So to study the number of credit hours taken by a typical student, Shauna asked the registrar to provide email addresses for 10 freshmen, 10 sophomores, 10 juniors, and 10 seniors. And then from each group, she asked for one whose student ID ends in 0, one who ends in 1, and so on. And so we want to know, what type of sampling is this? Well, we've broken down our population of what appears to be high school or college students into different but similar groups: freshmen, sophomores, juniors, and seniors. And so this would be a stratified sample, because then we choose at random based on random values of their ID numbers, and that is what generates our sample. The sample would likely be representative of the population because you're randomly choosing 10 people for each of the groups based on randomly assigned ID numbers. So the data that we directly collect for a statistical study are called raw data. Raw data alone can be difficult to interpret. Just having a list of numbers does not tell us much about the population that we're interested in. So in order to describe and draw conclusions, we need to organize the data in some kind of meaningful way. One way we can do that is what's known as a categorical frequency distribution. This is for when we organize data that are divided into distinct categories. like your class standing in school or conferences for college football teams. A categorical frequency distribution is just a table where you list the different categories and then show how many individuals in a sample fall into that category. So 25 volunteers are given a blood test to determine their blood type. So here we want to build a categorical frequency distribution. We have 4 different blood types here, A, B, AB, and O. And so we're just going to write these categories out, A, B, O, and AB. And now we just want to count how many A's are there. 1, 2, 3, 4, 5. So there are 5 A's. How many B's? 1, 2, 3, 4, 5, 6. How many O's? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then our AB's, 1, 2, 3, 4. And it looks like we missed a B. And so we'll just go add that here and make this a 7. And so now we have the frequency, or the count, the number of participants that fall into each of these categories. So using the data from the previous example, we can answer some questions. What percentage of the population would be expected to have an O blood type? Well, O, we have a frequency of 9. The percentage would be 9 out of 25, or 0.36, which is 36%. How many would we expect to have an AB blood type? There are 4 out of the 25 volunteers, which gives us 0.16, or 16%. Let's just try another example. A health food store recorded the type of vitamin pills that 35 different customers purchased during a one-day sale, and we just want to make a categorical frequency distribution. So our vitamin types A, B, C, D, and E. And now we just want to count how many of each letter. For A's, we have 1, 2, 3, 4, 5, 6. For B, 1, 2, 3, 4, 5. For C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. D, 1, 2, 3. And then for the vitamin E, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so here we have the categorical frequency distribution. Another type of frequency distribution is called a grouped frequency distribution. And this is where we have numerical data, and we take that numerical data and we divide it into classes. For example, if you gather data on the weights of everyone in your class, there's a pretty good chance that no 2 people are going to have the exact same weight. It's going to differ by some small amounts. If every weight is different, if we tried to make a categorical distribution, well then every weight has its own category. If you sample 30 people, you wind up with 30 different categories. You just have the same data set that you start with. You haven't done anything. So instead, when we have numerical and continuous data, it makes sense to group people into weight ranges. For example, 100 to 119 pounds, 120 to 139 pounds, and so on. In these classes, we refer to the lower number as the lower limit, and the upper number as the upper limit, or the lower class limit and the upper class limit. In order to construct a grouped frequency distribution, we want to follow a few particular steps. The first one is just to determine how many classes you want to divide the data into. This is generally set depending on the range of your data and how spread out all of your data values are. In order to determine the width of each class, once we know how many we want to have, we take the largest data value and the smallest data value and subtract them, and then divide by the number of classes that we have. And then this is important, round the value up to the next whole number. Always round up, regardless of what the number is. So if it's 2.1, round up to 3. We're then going to use the lowest number in your data, or a nice lower number that's close to it, as our first lower limit of the first class. We're then going to take the class width that we calculated, add it to the lower limit, and we'll be able to do that repeatedly to get the lower limit for all of our classes. We get the upper class limit by then just subtracting 1 from each lower class limit that comes after it, and then we just count the number of data values that fall into those particular groups or those particular classes. So we're going to use this data here on the record temperatures in each state in the country to construct a grouped frequency distribution. So the first step we want to do is to determine the number of classes that we want to use for this particular data. If we look at our highest score here, which is in California of 134, and then our lowest score, which is in Alaska and maybe some other places at 100, the difference between the lowest score and the highest score is about 34. To get nice round numbers out of our classes, let's use 7 classes. We had a range, which is 134 minus 100 of 34. 34 is pretty close to 35. If we divide 35 by 7, we'll have 5. And so just a nice round number. The number of classes that you choose matters, but you do get some say in how many you want to use. Some problems will tell you how many you should use. Now we want to find the class width. Well, the class width again is the largest number, 134, minus the smallest number of 100, and then we're going to divide by the number of classes. So we wanted to have 7 classes. That's 34 divided by 7, which is equal to 4.86. And remember to always round up. And so our class width is going to be equal to 5. Always round up. We then want to choose the lower limit for the first class. No values go below 100, and 100 is a nice round number, so we're going to choose 100 to be our lower limit for the first class. That's where our distribution is going to start. Now we want to determine the lower limits for all of the other classes. There are 7, so 100, and then we're going to add 5. 105, 110, 115, 120, 125, and 130. To find the upper class limits, we're just going to subtract 1 from the next lower limit. So the first upper class limit starts at 100, and if we subtract 1 from 105, it'll go to 104. The second class would go from 105 to 109, and then 110 to 114, and so on. 115 to 119, 120 to 124, 125 to 129, and then 130. And here we don't have 1 to subtract, but if we add 5 and then subtract 1, we get 134. So the smallest data value and the largest data value are represented. We have 7 classes, and they're all divided equally with a class width of 5. The final step is to determine how many data values fall within each of these classes. And so we need to go through and we need to count and figure out where these values fall. For example, 112 would be between 110 and 114. So we'll just write a little dash here as a tally. We're just going to keep track. 100 would fall in this column. 128 would fall in this column. And so on. 120, 134, 118, and 106. So I'm going to skip ahead here and complete the tallies, but you can do this at home as well in order to get some practice on how it works. And so here we have our completed count. To finish our frequency distribution, we just want to write the numbers. This is 3, 8, 16, 13, 7, 2, and 1. A histogram is just a visual representation of a grouped frequency distribution. The x-axis, in this case, represents the value that we're interested in. So for our example that we just did, the temperature. And the y-axis represents the frequency, or the count, how many were in each of those particular classes. Each class is represented by a bar of the same size. I notice all of these are the same size. And the height of the bar is equal to the frequency. 3, 8, 16, 13, just like we saw in the group distribution just a moment ago. And in a histogram, there should be no space between these different bars. They should be touching each other because this temperature is a continuous variable. And so we get a continuous spread of the data all the way throughout. There are two ways that you can make a histogram in Excel, depending on whether you have the frequency distribution or whether you're given the raw data. So in just a second, I'm going to pause and pull up Excel. You will have access to this file that I use in the video so that you can practice this. But I'm going to show you how to make both of these histograms depending on whether you're given the frequency distribution or the raw data. Do not automatically choose histogram from the chart menu and think that it's going to be correct. The histogram option is only going to work for one of these two different examples. And so we're going to do both, and then we'll come back and talk about the final example. So here we have a grouped frequency distribution. These values came from some randomly generated IQ scores. We want to find a histogram that will show the distribution of these scores and how they fall into each of these classes. To do this in Excel, if you're given the frequency distribution, we want to highlight all of our data. Go to Insert, and then we can go to Recommended Charts here. We want a clustered column, and so we're going to click on the one that pops up. So you can also go to All Charts and just go to Column, and you'll find it here. Hit OK. Now, as you'll notice, this does not look like the one from the notes. That's because we have to do some things to it to make it look right. First of all, we want to go to More Options here. And then up at the top, we click the drop down and we want to go to where it says Series, Frequency. And then you'll see if you click on these bars all the way to the right, if it starts here, you just want to click on the bars to the right. And where it says Gap Width, we're just going to take that down to 0. That will put all of our blocks together. And then we want to go here to Border, and we can choose a solid line. And I'm going to change the color to black so that it's easier to see. And now we have our histogram. We can do a similar thing if we have just the raw data set. But to make the histogram here, we want to highlight all of our data. We're going to go to Insert Chart. And this time we are going to choose the histogram. And then hit OK. Now this histogram does not look like the one we just had, but we can go to our options and go to Chart Options. We want to go to the horizontal axis. And then we want to go to our 3 bars here. We're going to go to Axis Options, and we want to choose the bin width or the number of bins. Either way, we know that the bin width in the previous example was 6. And now we have our histogram again. Looks exactly the same as the previous one, barring just some slight differences in Excel. So 2 different ways to produce the histogram, by either using the frequency distribution and a clustered column chart, or using the raw data and the histogram chart. Now we're just going to switch back to the notes and finish the last problem. So now you should be able to make a histogram if you're given the frequency distribution or if you're given just the raw data. Finally, another way to organize data is called a stem and leaf plot, or sometimes just a stem plot. In a stem and leaf plot, we split the data into 2 different parts. The stem, which represents the larger component of the data value, and the leaf, which represents the smaller component. For example, if we had a data value of 15, we might want the stem to be the digit that's in the tens place, 1, and then the leaf to be the digit that's in the ones place. If we had multiple values, then this would essentially group all of the data by tens. all of the numbers that started with 1 would be together, all the numbers that started with 2, all the numbers that started with 3, and so on. The choice of where to split the data value is determined by the numbers you're using. If you have a single value with a decimal point, like 4.3, well then maybe you split it by 4 and then 0.3, and so on. So it entirely depends on what numbers you have. So here we can construct a stem and leaf plot using data that's given for the number of cardiograms at a particular hospital over the course of 20 days. Stem and leaf plots are easier if you order all of the data from smallest to largest, and we've done that here. And so in order to organize the data, we're going to take the first number and the second number and essentially split them up. So notice 2, the first value here, or the number in the tens place, would be a 0. And so we're going to draw a line here. On the left-hand side, we're going to write the stems. 0, 1, 2, 3, 4, and 5. And on the right-hand side, we write the leaf part of the value. So 0, 2, we would just put a 2 here. 13 would be 1, 3. 14 would be 1, 4. And so we just list all of the leaves on the opposite side. 20 would be 2, 0. 23, 2, 3, and 25. And then 31, 32, 32, 32, 32, and 33, and then 36, 43, 44, 44, and 45, and then 51, 52, and 57. And so here we have a stem and leaf plot for this data. And you can see how it organizes the data by grouping them essentially by tens. And we have a good idea of how many values are in the region from 10 to 20, or how many are from 20 to 30, and so on. Make sure that you reference back to this video as you complete your lab for this week, and please let me know if you have any other questions.